Until recently, half the universe was missing, or hidden, or just undetected. And no, I'm not talking about dark matter or dark energy, which make up 27 and 68% of our universe respectively. No, I'm talking about normal, ordinary matter, which makes up you and me and the planets and stars and nebulae and basically everything you can see. And since most of this stuff is made of protons and neutrons, which are forms of baryons, this has been known as the missing baryon problem. We expect the universe to be made up of 5% baryonic matter, but when we go looking, we only find 2.5%. Now, the first question you're probably asking is, why should we expect the universe to be 5% ordinary baryonic matter in the first place? The answer is because with that density, we can explain the relative abundances of different elements that we observe in the universe, specifically the ratio of deuterium to hydrogen to helium. In the beginning, like right after the Big Bang, there were all of these neutrons and protons whizzing around. It was incredibly hot, and there was tons of radiation. The universe was radiation dominated. But as the universe expanded, it cooled to the point where protons and neutrons could start fusing together. A particularly stable nucleus to form would be helium-4, made of 2 neutrons and 2 protons. The problem was, to form helium-4, you first have to form deuterium, 1 proton and 1 neutron. And this is a less stable nucleus, and as quickly as it formed, it would get smashed apart. But by about 10 seconds after the Big Bang, the universe had cooled sufficiently that deuterium could form, and as soon as it did, it would rapidly fuse into helium. The rate at which this happened depended on the density of matter in the early universe. The higher the density, the faster this fusion could occur. Then, by 20 minutes after the Big Bang, the temperature had dropped low enough that fusion could no longer occur. And so at this point, the elemental abundances were locked in, like a snapshot of this moment. There was 75% hydrogen and 25% helium by mass, which is basically still what we observe in the universe today. Of the hydrogen nuclei, 26 out of every million were deuterium. What's amazing about deuterium is that it's stable, it doesn't decay, and there are no known processes that can produce it in significant quantities since the Big Bang. And that means virtually all the deuterium in the universe today, including the 1 out of every 6,000 hydrogen atoms in tap water, was created not in stars, but in the first 20 minutes after the Big Bang. When we look deep into space, the oldest light we can see is the cosmic microwave background radiation, the afterglow of the Big Bang, which has been traveling through the universe unimpeded since about 400,000 years after the Big Bang. And so we can literally count up those photons and work out the density of radiation right after the Big Bang. And using the value of 26 deuterium nuclei per million hydrogen nuclei, well, we can work out the ratio of baryonic matter to photons. And that is how we work out that there should be about 5% baryonic matter in the universe. So in the late 1990s, scientists went looking for all this baryonic matter. It was a census of sorts. They added up all of the planets and stars and black holes, galaxies, dust clouds, gas, basically everything you can see or infer exists using a telescope. And what they found is that everything that I normally think of as the actual stuff in our universe, it only makes up barely 20% of all the baryonic matter. So where is the rest? Well, not all ordinary matter is glowing brightly or is illuminated by nearby stars. It's not dark matter, but it is ordinary matter that is just in darkness. And so if you want to find those baryons, well, one way is to use a backlight, a bright source of light very far away, and that also means in the very early universe. And quasars are the perfect backlight. Their luminosity can be thousands of times that of whole galaxies. The light comes from the accretion disk of a supermassive black hole at the center of an early galaxy, as it engulfs all this matter. And since it is so distant, the light we receive from quasars is heavily redshifted.
For example, the light emitted when a hydrogen atom goes from its first excited state to its ground state, the Lyman alpha transition, it produces ultraviolet light of around 121.6 nanometers in a lab. But from a quasar, it can be observed as a peak in their spectrum at over 560 nanometers. That is yellow light. What's fascinating is if you look to the left of this peak, you see many little dips. These are absorption lines created by neutral hydrogen atoms that lie along our line of sight with the quasar. When light from the quasar reaches neutral hydrogen, the photons that can excite the electrons from the ground state to the first excited state are absorbed. This is the same Lyman alpha transition. But since these patches of hydrogen gas are closer to us, they are less redshifted. So the notches they make in the spectrum are at shorter and shorter wavelengths the closer the gas is to us. This has been described as the Lyman alpha forest. It's like a one-dimensional map that shows us where and how much neutral hydrogen gas lies along the line connecting us to the quasar. Adding all of that neutral hydrogen gas into our baryon budget brings us almost to 50%. So where is the other half of the baryons? Well, computer simulations of the entire universe suggested they are out there, just in between the galaxies in these sheets or filaments. And they're very spread out, just 1 to 10 particles per cubic meter. Plus, these particles are ionized, so they don't absorb the light like the neutral hydrogen gas. And they're in a temperature range between about 100,000 and 10 million Kelvin, a range astronomers like to refer to as warm-hot. So this is known as the warm-hot intergalactic medium, or WIM for short. But finding the WIM has been a real challenge. Because they're ionized and because of their temperature, they only emit or absorb in the high-energy UV or low-energy X-rays. Now, some people have used very sophisticated techniques to try to find the WIM, but then recently, a naturally occurring physical phenomenon allowed us to find all of the missing baryons. Let's find out how. First, we need to talk lightning. And I promise this is related. Okay, so did you know that it's possible to detect lightning from the other side of the Earth? This is because lightning produces a flash of electromagnetic radiation in all parts of the spectrum. I mean, we see the white light, but there's also broad spectrum radio waves which are released. And if you were nearby, you could detect those as a pulse. But the very low frequency radio waves can actually travel up and out of the atmosphere, and they get guided along the Earth's magnetic field lines out several radii from the Earth, and then back down where they can be detected in the other hemisphere. Except if they're detected there, they don't come in as a single pulse. Instead, they are spread out as a whistler. Now, if you play these radio waves through a speaker, we can actually hear them. So listen to this. You hear that descending tone that sounds like a sci-fi laser gun? Yeah, that is lightning on the other side of the Earth. So what's happening here? Well, as the radio waves travel through the Earth's magnetosphere, they encounter free electrons, which slows them down, and more for the lower frequency waves. This is dispersion. Just as a prism separates white light into its component colors, the plasma in the magnetosphere separates the radio waves into its component frequencies. Low frequencies are slowed down more than high frequencies. So what started as a pulse ends up as a whistler. And the amount of dispersion tells you how many free electrons that radio wave had to pass through to reach the detector. Now just imagine, we could do something very similar to find all the ionized baryons in the universe. All we would need is a bright flash of radio waves somewhere in the distant universe. And as if on cue, in 2007, astronomers found the first fast radio burst, which is just what it sounds like, a very short duration pulse of intense radio waves. And it came from the deep universe, from other galaxies. Now these pulses can be incredibly powerful. I'm talking billions or trillions of times as powerful as the sun, but they last for on order of a millisecond.
We don't really know what creates them, though some people suspect that it's magnetars or neutron stars or some sort of collision between these very powerful, massive objects like black holes and neutron stars. But for our purposes, all we need to know is that those flashes exist and that we can use them to look at their dispersion and figure out how many ionized baryons are between us and the source. And this is exactly what one recent paper did in Nature. They plotted out the dispersion measure of several of these fast radio bursts versus the redshift of their host galaxy. And what they found was, sure enough, the further out these fast radio bursts were, the more dispersed their signal when it reached the Earth. And in fact, using their measurements, they were able to estimate the total baryonic matter that is out there. And that includes all the ionized particles in the WIM, and they found that it was 5%. They found the missing baryons. Roughly 50% of them are in that warm, hot intergalactic medium. And so this validates what we had been thinking the whole time. You know what surprised me in making this video was realizing just how little of the ordinary matter from the Big Bang ended up in things like stars and galaxies, what I normally consider as the stuff of the universe. No, that's only like 10 or 20% of all the baryonic matter. So it turns out the formation of these interesting structures is a really inefficient process. But this finding is yet another triumph for science. Those computer simulations run decades ago turned out largely to be correct, and so everyone involved should be congratulated. But this also highlights for me the difference between scientists and non-scientists. I feel like non-scientists like being right. They like when things turn out the way they were expecting. But scientists, on the other hand, they want things to work out not the way they expected, because that's the way we get clues into what new physics is still out there to be discovered. I guess for now, we'll have to be content with being right.
Suscríbete a nuestro canal para disfrutar más contenidos.